Hello and welcome to another live stream from Portland State University's Learning Center. This is a Physics 212, that's Physics with Calculus live stream, and we're talking about a little bit more about electric fields, and we're going to go into electric flux and Gauss's law today. Just to get started, I wanted to paste a few links in our chat window here. So I've got a link to the Learning Center's website. On there you can find a bunch of different resources the Learning Center has for tutoring and other assistance they have. There's also a link to follow them on Facebook, follow them on Instagram as well. If you're here from your teacher, there is an attendance sheet, which is a form that I'm going to paste in there just now. I'll also paste this at the end of the lecture, so definitely try to fill out that form, let your teacher know you're here, and you might get some extra credit. All right, let's get started. Today, we are going to talk about the first problem, one of my favorite problems. We're going to have, in this case, it's a proton that's flying through a uniform electric field. So in this diagram down here, we have two parallel plates that are uniformly charged, and they have a uniform electric field going downwards between them. And the length of those plates is about 12 centimeters each. And we'll see that when a charged particle flies through there, the Coulomb forces are going to act on it, and it's going to push it downwards in this case, right? The negative side attracting the charged particle, and the positive side repelling it because it's a positively charged particle. And this problem is asking, when a proton enters the uniform electric field produced by two charged plates shown below, the magnitude of the electric field is 4.0 times 10 to the fifth power in Newton coulombs. And the speed of the proton when it enters the field is 1.5 times 10 to the seventh power in meters per second. What is the distance, d, that the proton has been deflected downwards as it leaves the plate? So this is a fun problem because it deals with electromagnetism, Coulomb forces, and then it gets back into what we learned in last quarter from kinematics and the basic ideas of motion in one or two dimensions. So let's get started with that. First things I want to do is pick apart this word problem, because word problems are always tricky where they give you a lot of information. You have to kind of digest what they give you and what you have to find out. So the first thing I see is we have a proton that's entering that uniform electric field. So that tells us what type of particle we're talking about. We know the charge of a proton, we know the mass of a proton. Those are standard values. You can do a quick Google search, look it up, and figure out what we're working with. We know the magnitude of the electric field is 4 times 10 to the fifth Newton coulombs. That's going to be important. And we know the speed of the proton is 1.5 times 10 to the seventh power in meters per second. And what we need to find, here's the most important, is the distance, d. And you can see the distance d is shown in the diagram down there. And that's the distance in which that particle is deflected. Because if it wasn't deflected, it would just travel in a perfectly straight line. But since there's a force acting on it going downwards now, it's going to arc. It's very similar to throwing a rock in an arc. It's going to arc up and come back down and drop. So that's what's happening. It's just, instead of gravity, we have the Coulomb force acting on this. So let's start to write out what we know. I know that the velocity of this particle in the x direction is going to equal 1.5 times 10 to the seventh meters per second. And that's pretty fast. In fact, that's about 5% of the speed of light. In this case, we're going to ignore the idea of special relativity and stuff like that because that's beyond this course now. You'll find out later that if it's anywhere past about 1%, you have small, minute, weird things happening with special relativity. But we're going to ignore all that for now. We know the distance that it's traveling in the x. I'll call it distance in x is going to be equal to 0.12 meters. Okay, as it travels through that uniform field. Once it leaves that uniform field, the force stops acting on it. So we only really have to figure out how far it's deflected as it's going through that field. And we can find out that based on that, the time it takes for it to travel through that electric field at that speed. And to do that, we just simply take the distance it traveled, 0.12 meters. We divide by the velocity, 1.5 times 10 to the 7th meters per second. And if we plug that into our calculator, first seeing that units are going to cancel, my meter is going to cancel out. I'm going to get a value in seconds. My S is going to come to the top. If we plug that into a calculator, you'll see it's about 8 times 10 to the negative 9 seconds, which is about 8 nanoseconds. Really fast. So it's only going to act on that. The force is only going to act on this particle for a very short period of time. Right? And in that short period of time, we have to figure out how far that it's going to be deflected downwards. Now we know from our problem up here that the electric field is equal, so the magnitude of the electric field is going to be equal to 4.0 times 10 to the 5th in Newton coulombs. And from that, we can derive the force of the particle. Because if you remember, there's a relationship between the electric field and the force, which is simply the force is equal to EQ, and this in the case is the charge of that proton. I'm going to go magnitude, so I don't have to worry about direction just yet. We know that since it's a positively charged particle here, and it's going to be attracted to the negative side, so it's going to be attracted downwards as it travels through that electric field. So we can figure out the force here. The force is going to be equal then to 4.0 times 10, this is the magnitude of the force, to the 5th power in Newton coulombs, times the charge of an electron, right? The charge of the electron is the same as the charge of a proton, or the charge of a proton, which is the same as the charge of an electron. So that's 1.6 times 10 to the negative 19 coulombs. And again, we notice that units are going to cancel out a little bit, and we're going to be left with a force, a value in newtons, which is what we're looking for. So if we plug that into our calculator, we're going to get a 6.41 times 10 to the negative 12th newtons. And for the direction of that, we can put, it's going to be in a negative j hat. So it's going down in the negative y. I can define my axis here as, I like to put this up on my diagrams, where this is a positive y and this is a positive x. So now when I'm talking about x and y, or I can even say this is a j and this is a I hat. So it gives you kind of those component vectors, that vector notation built into it. So we know the positive directions here, because we could put that axis at any which direction we want. Positive and negative can go left or right. It really depends on what we want to do with it. So now we have a force. This is the force that's going to act on that particle as it goes down. And it's going to act on it for a time of 8 nanoseconds. So the question then is, how far is it going to be deflected in those 8 nanoseconds when it's acting on that force? So we can go back to Newton's second law, where force is equal to mass times acceleration. Right? And here we know the force vector, we know the mass of a proton. Right? The mass of a proton I have is 1.67 times 10 to the negative 27 kilograms. So we can, from that, deduce that the force divided by the mass is equal to the acceleration, which, if we wrote that out, would be negative 6.41 times 10 to the negative 12 newtons divided by the mass, which was 1.67 times 10 to the negative 27 kilograms. We could plug that into our calculator and get a value for it, and we would get a negative 3.83 times 10 to the 15th meters per second squared. And this acceleration is going to be in the same direction as our force. Our force was in that j hat direction, so our acceleration, this is our acceleration here. So now we have a value in acceleration. Now from just that acceleration, we can then go back to our basic kinematics problem. If you remember, in kinematics, we had the equation where there was like a delta x, and in this case I'm going to say delta y, is equal to the initial velocity times time plus 1/2 acceleration. These are all vectors, time squared. That was one of the main kinematic equations we use to determine velocity, acceleration, time when we're dealing with a lot of these things. And in this situation, we know the initial velocity in the y direction was 0 because it was going in a perfectly straight line. So we can say, okay, we cancel out this first term. We now have solved for the acceleration and we know the time, which means that we can solve for delta y, which is equal to 1/2 times our acceleration, negative 3.83 times 10 to the 15th meters per second squared, times our time, which is 8 nanoseconds. That's 8 times 10 to the negative 19, or not 19, 9 seconds. And that will equal, when you plug it into our calculator, I got negative 0.245 meters. So that's the amount of deflection that happens when a proton enters an electric field. That's negative, it's going downwards is the negative, and then it's 0.245 meters, or 24 centimeters. And I like this problem especially because something very similar to this is how they first discovered the electron. J.J. Thomson back in the late 1800s started realizing that if he heated up this plate of copper, I think it was, he could detect something flying through. And when he put a magnetic field through, or no, sorry, an electric field through there, he could deflect that particle left and right, proving that whatever he was pulling off of this metal plate had a charge to it. And he happened to be pulling off electrons, which was one of the first discovery of a fundamental particle. That was before we actually knew what an atom looked like. So it was really a groundbreaking discovery, and I really liked this experiment. And it's a cool way to tie in your electromagnetism with kinematics and what you learned in Newton's laws and stuff like that from the first quarter as well. So now we're going to move on into flux. And flux is a fun beast. So flux is literally how much of something goes through a given area. In this case, electric flux is what we're going to focus on, and electric flux is the amount of the electric field which travels through a specific area that we're looking at. And the area that we're looking at the flux is going to be determined based on the angle difference between the electric field and that area. So if we look at these two diagrams that I have here, in number A, we have surface 1. Surface 1 it's going to be in the x, it basically is the zx plane. It's in that zx plane, and the electric field is moving perpendicular to it, or orthogonal to it. So as the electric field goes through, we can calculate the amount of it based on the surface area there. And we can use these equations that you should see pop up above me now. Specifically, the flux for the surface is equal to the electric field dotted with the area. In this case, E times A cosine of theta, where that cosine of theta is equal to the vector of the electric field and the vector of the normal vector coming out of that area. In this case, that vector is going to be 0. So we can simply calculate that by doing the magnitude of the electric field times the area, and it gives us the flux, because there's no angle difference between them. But if we compare that to S2 over there on the right hand side in B, notice that we now have another surface. This one's at an angle from the first one, and it's kind of set up on the top of that first surface, laying down until it intersects the XY plane. And this is a really good example because the angle now, theta, that's coming out from the normal vector, which is an orthogonal vector coming out from the plane, theta is going to be the angle between that and the electric field. And because there's a slight angle there, we can see that we're basically looking at like a projection of this angle S2 in the XY plane, some perpendicular plane, to pick up the same amount of electric flux going through there. So in this instance, the electric flux through S1 is going to be equal to the flux through S2, which is equal to EA cosine of theta. We don't have values for these, so we can't calculate them, but we know that that would be a good formula to use for any type of surface that we're dealing with. And this leads to discovering and using Gauss's law, which instead of having just a surface of flux, we're going to enclose our charges in a Gaussian surface, this imaginary surface. All of these surfaces are not real surfaces. They're kind of imaginary surfaces. We can imagine some area here, which we can define, and we can calculate how much of the electric field would be piercing through that. So same with these Gaussian surfaces, which are enclosed shells of weird shapes even that are surrounding different charges. And we could do a surface integral of that based on, again, the second equation above my head. We do a surface integral of the dot product of the energy vector, or the electric field vector dotted with the dA, the area, and it's going to give us basically the charge enclosed in that surface divided by epsilon naught, which is a constant permittivity of electrical space in a vacuum. So since it's a constant value, that Q enclosed equals epsilon or over epsilon naught, it's a really easy thing to use, so we can surround any charge or group of charges with this Gaussian surface, and we could determine then what would be the flux of that. And based on the flux of that, we can then backtrack and find the electric field. So it's a useful way of knowing the enclosed charge to determine the electric field as well. And I'm going to show off some great simulations. I love simulations. If you've tuned in, you know I like simulations. I'm going to jump over to this guy here, which you might have seen. This lets us kind of drag this orange surface, or sorry, this green surface around. And you can see in the middle we have a positive charge. We can tell because the vectors for the electric fields are going outwards. And if we drag this around, the gauge on our left-hand side tells us the magnitude of the flux. And you can see as I get over there, boom, we have flux because it's inside the surface. Boom, we have no flux. So it's really just an on-off procedure. There's no changing the value of it, as long as that charge stays steady. And we can change the types of surfaces we have. We have a smaller surface, okay, same thing, same value for flux. It doesn't change any. Going back here, it's the same value. It doesn't matter how big or how small that circle is, it's going to give us the same amount, because it's the same amount of electric field going through. The density of the electric field is denser at that area, but you have a smaller area. For the green surface, you've got a bigger area now, but the density of the electric field is slightly less. We can switch to this orange surface. This is a square, not a circle anymore. Still, the same flux. Nothing's changing in there, right? Because even though it's a square, you have a certain amount of flux going out this way, and this way, this way, and this way. It's all coming out. We sum up all of those sides, and we get the net flux for the whole thing. And it's going to be the same thing because the charge enclosed is not changing. Switching to this blue area. Here we change the charges, and we can see looks like there's two charges in here, right? One of them's negative, one of them's positive, because I can see some arrows kind of floating down between these, connecting them up. If I grab this and go over it, you notice there's no flux. That's because there's one positive and one negative charge. We have a net charge of 0 in there. That net charge of 0 says that the charge enclosed, 0 divided by epsilon naught, still 0. So the flux is equal to 0. Switch over to another simulation that I like. This one's a similar idea. We have a square surface here. We get to see the electric field vectors kind of shooting out of it. And this actually calculates the flux on the top, the left, the bottom, and the right. And if we add up all those numbers, we get this value in the middle. And I can actually grab grabbing a hold of the wrong thing, grab a hold here, and we can see those arrows kind of change. So you can see the electric field coming out of this top left corner is a lot bigger. We're getting some nice positive numbers here, nice positive numbers here, kind of a small negative there, and a bigger negative here. Okay. And you can see how it kind of changes, but you see the net stays 0 no matter how I move these inside, right? And that's because the lambda 3 that I was just dragging around here, that's -2 nanocoulombs per meter. That's the density of that little ball. This one up here, the lambda 1, it's the same, but it's positive. Right? So the positive one is radiating electric field outwards. The negative one is sucking it inwards. But either way, the net flux is the same because the charge is there. If I moved another charge in, boom. Okay, now I get, it's going outwards almost everywhere except for this top right corner near where my negative charge is, but my net is no longer 0. My net flux actually has a magnitude now because my internal charge, the enclosed charge, has become 2 nanocoulombs per meter as opposed to the original 0. 0. So this is a fun simulation to play with. If anyone is interested in playing with it, I can post a few links in the chat as well for this one or this one. I like playing with simulations. It helps me kind of understand and see what's going on. For that second one, you can change the charge of the different change the charges that you put in there. You can move it around. You can say even like, okay, these are both going to be about 1. This is one thing I like to do is, even though there's 2 charges in there, if those positive charges are half the magnitude, what happens to the net? The net is going to still be 0. Even though I've got this one -2 in here, which is really big, and I've got this +1 and this +1, the internal charge of that is 0, so the flux coming out of that surface also going to be 0. And that's a key part of Gauss's law right there. So let's move on. We're going to look at a few examples. Let's go. And we're going to try to determine, based on these, what the flux is going to be. Is it going to be positive? Is it going to be negative? And what's the relationship of the flux between different things? Just to kind of evaluate them as best we can. In this first one, A, we have a positive charge sitting over here on the side, and you can see it's radiating its electric field through the surface. It's going through the surface at least 3 different points, probably various points in between as well. And it's going to enter the surface here, enter the surface, and it's going to leave the surface here, leaving the surface. So the same amount of electric field has entered as has left. So the net flux on the whole thing is equal to 0. We can see that just based on the nature of flux. If we compare that to Gauss's law, the net charge inside is equal to 0. So the flux is equal to 0. So Gauss's law corresponds to what we observe based on the electric fields going through the surface. Looking at part B, this is similar to the simulation with the blue circle. There, we have a positive charge and we have a negative charge. And you see there's some electric fields going between them, and we have some electric fields going in. You have the same amount going out, as long as those 2 charges are the same magnitude, right? So if you add up the charge 1 and add up charge 2, and together the sum of those charges equals 0, then we know we have no internal charge there. So we can say that there's no flux. So the flux for this is also equal to 0 based on Gauss's law. Looking at the third one, part C down here, we compare, there's 2 surfaces here. There's S1, which I'm going to say is this one here, and there's S2, which is this weird funky shaped one out here. And notice, to find the area of that weird funky shaped one would be a calculus nightmare. You'd have to have equations going, surface integrals going this way and that way. It's a lot easier using Gauss's law to just say, well, what is the enclosed charge? The enclosed charge for S2 is just 1 positive charge. The closed charge for S1 is also that 1 positive charge. So we know that the flux is equal to both of those. So even though I have this weird shape, I can just simplify it and do a surface integral for a small sphere if I had to figure it out. But I know based on Gauss's law that the Q enclosed over epsilon naught will equal the flux. Whatever that charge is inside, if it's 1 coulomb or 1 nanocoulomb, we can plug that in. We can get an answer for flux real quick and easy. Let's look at a few more examples down here. This first one is pretty simple. We have 2 microcoulombs there. We can calculate that because that's going to be just enclosed charge 2 microcoulombs divided by epsilon naught. Then that's going to equal our flux. The second one, now we have a negative charge. The only difference now is we have negative 2 microcoulombs divided by epsilon naught is going to be that one. This one up here, we've got a positive charge here that's 4 microcoulombs. That's pretty big. And we have a negative charge here that's negative 2 microcoulombs. And we have one over here that's positive 2 microcoulombs. This is for part C. And we see the enclosed space is S, which is only really enclosing that positive 2 microcoulomb charge. So we can say that, simply put, the flux based on Gauss's law is equal to 2 microcoulombs over epsilon naught. These charges out here, they don't apply to finding the flux of that. They do affect, they have a electric field, and their electric field vectors definitely do intersect that, but for every one that goes in is also going to come out. And you're going to have some weird fluctuations of electric fields going on between these positive charges, for example. You're going to have current or electric fields flowing from one to the other here as well. But for everything that goes in, it's also going to come out for all of these 2 charges outside of the field. So the only charge we really have to worry about is this guy in the middle. That's the only one that's going to add to our flux. Similarly, now we have this big guy down here. Well, this charge, this negative 5 microcoulombs and this positive 4 microcoulombs isn't really enclosed. This positive 4 kind of looks like it's enclosed. It's surrounded, but it's not enclosed. Everything that's going to go in, it'll go in at all these directions, but then it'll come out, as well in all the same areas. So its net flux to the system, that's 0. The net flux of this one's 0. The only ones we have to worry about is these guys here. And if we add these guys up, that's 6 minus 4 minus 1 is equal to 1 microcoulomb. These are all microcoulombs. So that would be 1 microcoulomb divided by epsilon naught. And that's going to be our flux for that situation. Going over to part E, this is the cube now. This cube is similar to the last one. It's got 3 charges inside of it, 2 charges outside of it. In this case, we can add up these 3 charges. 4 plus 6 is 10, minus 10 is 0. This hole has 0 flux. We don't have to worry about anything outside of those. So Gauss's law is a really simple and easy way to calculate and determine the amount of flux going through a Gaussian surface, which then can let us backtrack and find the area of that surface if we know the electric field, or the electric field if we know the area. It's a useful tool in those regards. So we're going to move on. This is going to be a little bit more complicated now, because now we're looking at a Gaussian surface that is going through a long cylinder, and it's a uniformly non-conducting cylinder. So in this case, the charge enclosed, so Q enclosed, is going to equal the lambda, the charge density enclosed by our surface, times L. Okay, so the charge density is how densely things are charged on this thing, and we're going to multiply it by L because that's the height of our cylinder in a way. And we can also say that that's equal to, say, the surface density enclosed times the area. And then we can use the electric field equation, which is in this case going to be E is equal to lambda enclosed divided by 2 pi epsilon naught times 1 over R. And notice that's really similar to what we used in when we had that infinite line charge, right? Because we're looking at the electric field coming off that infinite line. That equation was 2k lambda over x in the I hat direction. Here we have r because we're just going in a radius outside of that. And notice our Gaussian sphere is this blue colored cylinder here. And it's intersecting our long, it's a kind of a uniform long conducting wire, or non-conducting wire, or cylinder in this case. Wires are basically just a long cylinder. So these look fairly similar. Our electric field is going to be calculated in a fairly similar way. But now, instead of having just a point charge on that line, we actually have this surface of the wire going around it. So when we calculate that, we can say that the charge density of the enclosed is equal to sigma naught 2 pi r L divided by L. So remember, normally sigma naught is, or sorry, lambda is going to be the charge density of a line. And that charge density is the charge divided by the length, right? Charge per length of the wire or the line you're going through. In this case, our charge is really a surface area, so we switch it to sigma, which is usually the charge divided by the area. Well, in this case, we have sigma sigma 2 pi r is going to equal the charge. In this case, we plug that in for our charge for lambda over L, and we're going to multiply it by L, so we can actually get that the height of it. The 2 pi r is going to be the radius or circumference around that wire, multiplied by L gives us the height, and we get the full surface of the integral there, or the wire. And if we simplify this, canceling our L's there, this is just equal to sigma naught 2 pi r. Now, we can plug this in to our electric field equation. The electric field is equal to sigma naught 2 pi r divided by 2 pi epsilon naught 1 over r. It's going to be in the r hat direction. Just the direction of that electric field is going to shoot outwards in the direction of the radius in this case. Simplifying some more, the 2 pi's get to cancel out, and we're left with sigma naught, our charge density per area, times our radius, and that's the big R, which is no, I guess that's the radius of the wire up there, because little r is our vector, divide by epsilon naught 1 over r. So that is a really simple way to figure out the electric field coming off of an infinitely long wire. Just by using Gauss's law, we can, it's a lot easier than doing the complicated integrals that we were doing last week for this infinitely long wire and stuff. We can just look at what's the charge enclosed in this, and we can plug that charge density into the charge enclosed for that section, and we can figure out the electric field. Looking at a different Gaussian surface, this one is actually inside that wire, notice. And once we get inside that wire, we look at the charge enclosed. It's going to be equal to 0. So anything inside that wire has no charge to it. So the flux is going to equal 0. Therefore, the electric field is going to equal 0 as well. It's a pretty good use of Gauss's law, and it's a way to determine the electric field in a lot easier manner. That is all I actually have for you today. We kind of flew through that. If anyone has any questions who's watching, feel free to throw it in the chat. I have drop-in tutoring hours through the Pingy app from 2 o'clock to 3 o'clock. So feel free to stop in there if you have any more detailed questions or you want more one-on-one time. I will also post a repost that link for the attendance sheets. So if you wanted to fill out a form to let me know, let your teacher know that you came, feel free to do that. And if there's no questions, I'll see you all next week. Have fun.